what do we know about a particular Qualia structure? So structures of Qualia have been studied in some domains. And in particular, colors, tones, and orders, and many other things have been characterized through similarity rating. But it's actually time consuming to examine this kind of structure. If you think about it, if you have 10 stimuli, and if you use standard kind of experiment like naming or discrimination and so on, then each time you try to examine the relationship or similarity and so on, it costs more than the single trial to do that. If you have 10 stimuli, then all combination of 10 stimuli would be like already 100 trials. So it's very time consuming. And so as a result, not much is known so far. However, over the last decade or even a few years, online version of the experiment has started to become very, very good. And so I think it will be sooner or later to know about this type of the structure in many different domains. Okay, and some assumptions in the previous studies may not be valid. That's actually quite an important thing to note, and that relates to what I said in the last lecture video. So this structure, the ring structure of color Qualia similarity, that is a sort of the basis of also Ariel's experiment of the color equivalence between fovea and the periphery. But these kind of color similarity structure has been established through the studies that used pretty kind of coarse kind of method. And for example, they didn't control the duration of the presentation so that people can move the eyes, and also eccentricity was not really fixed, and then duration was also controlled, and then size was also presented at the same size at the fovea and periphery, and many things, and attention and expectation was not controlled. So people continue to say that, oh, we are actually experiencing, we feel we experience a color, but it's mostly expectation or memory. But even if we control the random position and also duration, we still observe this kind of color Qualia similarity ring, right? That's what Ariel has shown. And also we didn't have previously this kind of the display. So here you can sit in front of the 360 or 180 degree half dome type display, and then look at the center of the display. So here it's almost like this portion is the standard display, computer display, but we can present the patch like here at the very, very periphery, and then try to see whether we can still experience color in the way that we expect in terms of color ring structure. But these are the things that we really don't know yet. It's an ongoing project. Okay. But even more fundamentally, there are some interesting things that are emerging over the last 10, 20 years. Many psychological models implicitly assume that quail, or the way we perceive things, is something like a point in high dimensional space. And then dissimilarity between the two experiences is probably something like a distance between the 2 points. That's the sort of the many people's intuition, or at least that's the implicit assumption of the models that you have possibly seen in other people's presentation. But here the question is this really reasonable? Okay. And here the important thing is to consider is the assumption based that is behind this points and the distance kind of framework. And distance or metric is a concept, mathematically speaking, that has to satisfy three fundamental properties or axioms. And one is a minimality. When you have a point A and then another point A, or itself, the distance between A and itself has to be 0. It makes sense, right? And then secondly, symmetry. If you measure the distance from A to B, then the distance from B to A is also the same from A to B and B to A. That makes also same sense. And then finally, triangle inequality. Distance from A to B and the B to C has to be always larger than A to C. So this is a bit difficult to imagine. So I'll just explain. So in a sense, when there is some kind of points A to C, it's always a case that it takes more time or more distance effort to go through some points, and that's a triangle inequality. It makes sense in a sense, right? But does this actually make sense for Qualia? The Qualia similarity? You need to think about it. And at least minimality is already weird, right? If you think about binocular rivalry or visual illusions that I have been showing for many, many times over the course of this lecture, same thing doesn't need to be, perceived as the same. Like, this Necker cube that over the time, it doesn't look the same. So if you consider A and A as some external object at time t, and time t2, then now the same object doesn't have to necessarily, be seen as similar at all. And even if you show two physically same thing at the same time, people do not say that they are the same all the time. That's known across many psychological literature. Okay, and the symmetry, that's also the thing that we are going to talk about. And triangular inequality is a bit complicated, but again, these three things are something that is not come for free. And in particular, this violation of the symmetry in similarity has been noted by Tversky. His 1977 paper is very interesting. And Tversky is the long-term collaborator of the Daniel Kahneman, who has written, fast, slow, this very important kind of, books on the cognitive bias, and he got a Nobel Prize in economics, right? But Tversky has found that the symmetry of A and B is quite easily violated in the case of the perceptual decision. So if I ask you, for example, most of the audience here would say that if you are asked, is North Korea similar to China? Most of you guys say, yes, it's similar in the level of, let's say, 6 out of 7, right? 7 being most similar. But if you are asked, is China similar to North Korea? It feels like it's really weird. And at least for me, I would say, no, it's not similar at all. So maybe 3 out of 7 similarity. And this has been empirically shown many times that many people say no. The above kind of question, yes. Below kind of question, no. So this means that there is an asymmetry in similarity judgment. So North Korea to Korea is similar, but China to North Korea is dissimilar. It's almost like energy consumption for climbing up the hill, right? So going uphill is difficult, but coming back from hilltop to the bottom is easy. But this is not the kind of the distance that we are thinking of usually. Okay, so to address this question at the level of even the color patch, Beth Fisher in my laboratory has studied this empirically. What she did was to show some kind of a color patch like here, pink, and then afterwards showing another color, green, and then asked people how similar the second one is to the first one. Okay, and this is the result. So if you look at this, then it's very similar to what Ariel has found already. So the same color, red, and orange, and so on, all these diagonal are highly similar, but there is some points that are not 100% same, right here. This is not completely white, which is the violation of minimality, which I'm not going to focus on here. But if you look at this very carefully, then it turned out that, for example, this one, like after showing this bright green, if you are shown the sky blue, then you tend to say the dissimilarity of maybe 4 or something like that. But if you see sky blue first and then see this bright green, then it feels like it's a more dissimilar. So the dissimilarity of 3 or something like that. 4 becomes 3. Okay. Another example here is that after seeing this orange, seeing pale green, you say, oh, it's very different. And the dissimilarity is maybe 4 out of the 7. But if you're shown this bright green first and then shown orange, oh, it's even more different. It's even more dissimilar. It's like 7 on the 5 or 6 out of 7. And this turned out to be highly consistent across many people. So in this case, it's 40 subjects in a preliminary experiment. But these are, we did a very conservative statistics, but still it's quite significantly different. So what are the available options for the color-Qualia similarity structure to explain or think about this? The classic way to think about this is always pretty much the points in some high-dimensional space. Here, let's say in the case of two-dimensional projection, this is a potentially location of all these 9 patch, and then the distance between these two corresponds to all this dissimilarity. That's called multidimensional scaling. It captures quite a bit of the variance, but this kind of model doesn't tell us anything about whether green than orange has to be more dissimilar than orange than green, right? There's nothing to explain this. The alternative structure that has been proposed is this quantum model. In the case of a quantum model, points are replaced by this thing called subspaces. It's like arrays, in this thing. And then instead of the high dimensional space, what they think about is that in some vector space. So if you're not familiar with physics or mathematics, both subspaces, vector space, quantum may feel really weird, but what I wanted to deliver is that the left side classic approach is not the only one that has been proposed as a Qualia structure. And which one is better is some empirical question, actually. Okay. And in the case of the quantum structure, what has been proposed is that the similarity, it has to depend on the way you project the initial state. So measurement of A and then B is not the same as a B then A. And in the way particularly projected predicts how they are similar to each other. So just to give you a very vague but a good intuition, this figure serves a good purpose. So let's assume that your initial mind state or conscious state is here. It's you read it as psi, and then this psi is now first projected onto, let's say green or maybe blue. I don't know. Then what it means is that you first get this position, and then you project it to another subspace, which is the, let's say orange instead of A. Okay, then the green-orange similarity depends on this vector. On the other hand, if you first get shown the orange, then you first go there and then project to the green, and then that's the result of the orange then green. And then as you already see, the length of this green then orange is much shorter than the orange then green. And that is precisely the quantum model's prediction about the similarity and symmetry. And in fact, the data that we have now seems to be much better explained by this kind of model than the classical model. We'll see how it goes, but it seems one of the most powerful alternative to this classical point and this dimensional kind of thing. If you think about it, our conscious experience is to think about it as a point itself is already weird, really weird. The only advantage of the left side is that it can somehow feel like intuitive because it is easy to understand and it's something that you have been exposed to through the education and mathematics. Right side is more weird because most of the people have never learned the quantum physics. But once you get used to it, may not feel really weird. And if that explains our conscious experience, that's the kind of standard thing that we need to learn, right? So we'll see how it goes. But in summary, even the most studied Qualia structure is not well understood, and models that assume a simple distance are not compatible with empirical similarity ratings, at least in our hands. But there are many other examples. And the quantum cognition is something that is very interesting framework that has started over the last decades or so. But it seems to explain quite a bit of the many different kind of perceptual or cognitive and many different kind of biases that we usually cannot explain theoretically, right? So we need to probably have another lecture series for the quantum cognition, but let's stop here. But okay, if we understand the Qualia structure better, what's the next step? That's the next video.